The goal for today is to try to get about half the review done. I'm not going to go through every single question today. I am going to leave some for tomorrow, but hopefully I'm not going to leave any for Monday. I'm really going to leave that open for you guys to say, hey, can you do another question like this in the review? Can you do another question like that? And I'll think of them on the spot, and we'll just go from there. And then whatever you have time left over, you just review on your own. But again, that will be on Monday of next week, because then our exam will be on Tuesday, Wednesday. And again, you can kind of treat it like half and half, part one and part two. There is not a no calculator portion to the exam. It is just everything is full calculator. It's just half the material and then half the material. All right, nothing to it but to do it. Any questions before we begin? Here we go. All right, so given f of x, find all of this junk. This is all the way back to chapter 1, right? I've got this piecewise looking function thing. What is it telling me to do in A and B? When I find f of -1, what's it telling me to do? Find the what? Find the y value, right? So where the x value is -1. So -1 here. I'm just going to write these in so we're sure. This is -1, -2, -3, -4. This 0, 1, 2, 3. Okay, here we go. So f of -1 should be what? 0. Pretty easy there, right? What about f of 3? Looks like it's -1. I'll write that in, -1, 1, 2, 3. Looks like it is -1. Okay, now, f of x equaling -1. Now I'm giving you the y value, asking you to find the x value. So flipping it on its head a little bit. So finding the x value when y is -1, well, you got to kind of look down here. Right? What two x values have the y value at -1? 0 and 3. X equals 0 or 3. Either one of those is fine. Or and 3, I guess you could say. F of x is equal to 1 when x is equal to. Okay, so now looking here, looks like there's two places again. Once right here, and then once right here. Looks like it's about a little bit less than -1, so we could estimate it to be about -1.2, and or -4. You know, it's interesting. We talked about increasing and decreasing way back in chapter 1, but we really didn't know what the implications were of it yet, right? We know that where the interval is decreasing, the slope is negative, which means the derivative would be negative as well on all of these pieces here. So it looks like it starts going down from -2 and then stops going down all the way at 0. I know something weird happens at -1. It kind of shifts a little bit. It looks like there's a little bit of a corner point there at -1, but I really don't care because it's still decreasing, right? From -2 to 0. From -2 to 0. I was debating on whether to do a parenthesis or bracket there, but again, at -2, it is not decreasing. It is at its apex point. So from -2 to 0 would be decreasing, and then there's one more spot from 1 to 3 as well. From 1 to 3. And then the domain and range. We've been doing this since Algebra 1, right? Domain looks like I'm going all the way from -4 and all the way to +3. -4 to +3. And I would put brackets around this. And then the range looks like it's going from -1 all the way up to +3. -1 to +3. Questions there? Okay, let's take a look at question 2. Given the piecewise function, find the following information, then graph. I probably will give you something better to graph than this one comes out to be. You know, this one comes out to be way up off the top of the graph, so I did not mean for that to happen. That's okay. You know, I'm just going to remake this graph instead of using a 10 by 10. I'm just going to remake it because that does not come out nice. All right, but let's remind ourselves about some piecewise functions. Remember, it breaks at 5. You see that there? It breaks at 5. And know again that piecewise functions don't have to connect, right? Piecewise functions may have a discontinuity in them. That's okay. So for example, if I want to find f of -5, we just say, okay, well down here, It's got to be negative 5, less than or equal to 5, down here, using this rule. So 2 times negative 5 minus 13, minus 3, excuse me, minus 3. That's negative 10 minus 3. You guys get negative 13?
Yeah.
Now, which rule do I use, top or bottom, for f of 5? Bottom, because it's got the or equal to. So 2 times 5 minus 3. Okay, that's 10 minus 3, or 7. What would it be like if your math teacher only spoke Spanish? Take a look at 7 now. Again, it would be x is greater than 5. So we plug that in. X squared plus 1, 49 plus 1 would be 50. Okay, now I'm going to kind of just sketch the graph. Looks like I want to go past 5 a little bit, because I know that's the breaking point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. It doesn't really matter over there. Now, I know I have to go all the way up to 50, right? So what I'm going to do is I'm going to go by 10. So I'll just say 10, 20, 30, 40, 50, 60. And then we'll say negative 10, negative 20. All right. Taking a look here, if I want to just graph the linear on the bottom, remember that it breaks at 5. 2, 3, 4, 5. Okay. If I want to graph the linear on the bottom, 2x minus 3. I know the y-intercept's at negative 3. I know those slope's going to be 2. But since I kind of distorted the graph a little bit, it might be better to just use the coordinates. For example here, negative 5 comma negative 13. 1, 2, 3, 4, 5, negative 13. Somewhere down here. Yeah. It's a big dot for that. And then 5 comma 7. 1, 2, 3, 4, 5 comma 7, somewhere here. Again, I've distorted the graph a little bit by changing the scale on the x-axis or the y-axis. So, that's why it looks so weird. Okay, now remember that this quadratic, this x squared plus 1, is that going to connect with this line here? No. And I remember back when I was grading a lot of these tests, that's what the issue was a lot of the times. People thought, oh, it was quadratic, so it's got to just go like that, right? Because it connects. No. So go back. There we go. So what I have to do is say, okay, where would it be if I use the top rule at 5? 26. At 26. So really, this open circle is at 5 comma 10, 26. Somewhere around right there. And then you can kind of just sketch the quadratic past that. I know it's got to go all the way up to 5, 6, 7 comma 50. 10, 20, 30, 40, 50. Something like that. I know it's going to curve up. Do I need the dotted line there? No. I like to put it in just because I know that there's a discontinuity there, right? It doesn't connect. All right. Oh, remember this one, the one with the table, the F, the composition, F of G, G of F. These are fun. So taking a look here at the first one there, G of 20. So the first thing that I have to find is G of 20. So here's the X value at 20. So G of 20 would be 41. So in other words, G of 20 should be just G of 41, which is essentially just 20. Gets us back to 20. And then I have to find G of F of 59. So G of F of 59. F of 59 is 55. So this is just going to be G of 55. Which G of 55 is 38. Pretty simple there. Okay, let's take a look at number 4. Evaluate the following limit. Now remember, your first line of defense for limits. Your first line of defense is direct substitution. That's your first line of defense. If you can directly substitute, And in this case, I can. Like if I plug in 2, I have the square root of 2 plus 7 minus 1 over 2 times 6 minus 4. So that gives me the square root of 9 minus 1, and then over 12 minus 4 is 8. So 3 minus 1 is 2. 8 is 1/4. That should always be your first line of defense, is to try to directly substitute. If you can't directly substitute, then you're going to have to do something different, which is the case in number 5. Like here, if I tried to directly substitute, the bottom would make me freak out, right? 3 squared minus 9, that's 9 minus 9, that's 0. I cannot have 0 in the denominator, so you cannot directly substitute. So what I'm going to do is try to manipulate that down a little bit to see if I can manipulate it into something that will directly substitute. So in this case, x squared plus 2x plus 5, or sorry, minus 15. Sorry, I was thinking about the factored portion of the first. Plus 5 minus 3, right? Plus 5 minus 3, factors of negative 15 that had to get to positive 2, positive 5, negative 3. And then that's still over x plus 3, x minus 3, right? X squared minus 9 is the difference of squares, so it's plus 3 minus 3, which we see that the minus 3's will cancel out. Leaving us with the x plus 5 over the x plus 3. And can we directly substitute now? Yes. Plug in the 3, I get 3 plus 5 is 8, over 3 plus 3 is 6, so 4/3. All right, let's take a look at number 6. Now remember, the past two were different from number 6 because for both of these past two, it was a definite limit, right? X going to 2, X going to 3. I knew that was going toward a number. This is an infinite limit, right? This is an infinite limit, which makes our life a little bit more difficult. But it's nice when we have this fraction here because what we can do is divide by the highest power in the denominator, which means x to the 8th. Hold on, let me shut the door. Sounds like great. Okay, minus 8x over x to the 8th plus 6x to the 3rd over x to the 8th plus 12x to the 4th over x to the 8th minus 6x to the 8th over x to the 8th, all divided by 18x to the 8th over x to the 8th plus 2x squared over, should have put that 2 up in the top, doesn't matter though, over x to the 8th minus 15 over x to the 8th. Now, the reason I'm doing that is because now, when I evaluate the limit going to infinity, when you have a denominator that will get infinitely bigger, what happens to that term? Goes to 0. Like, if I keep making x bigger and bigger and bigger and bigger, that means it's going to get me 2 over a really, really, really big number, which will eventually make it negligible. So that's going to go to 0. This is going to go to 0. This is going to go to 0. This is going to go to 0. Will that end term go to 0? No, because this ends up being a constant, so which ends up being just a negative 6 on the top. This is again a constant, just an 18 here. This is going to go to 0. This is going to go to 0. So really, I'm all left with negative 6 over 18, which is negative 1/3. All right, so let's take a look at this one. Remember these? So finding the limit in a graph. Finding the limit within a graph. First one here, the limit as x goes to -4. Okay, now remember, this is the x value that I want to find. I want to find the y value when x is -4. So if I go to find -4, the function is right there. If it's a concrete point, if it's within a line, if it's continuous, then you know it's just going to be that y value. So in this case, -4 comma -3. 5 comma 1, 2, 3, 4, 5. Okay, I'm just going to say that that's -4. If you said like -4.1, I wouldn't be mad at you. Okay, limit as x goes to 7. 7's over here. Looks like that's 6. Now, remember that this notation means going from -2 to the left, right? So if you're looking at -2, you want to look on the left side of -2. So in this case here, on the left side of -2, I'm looking at it right there. So on the left side of -2, it's going toward -3. Do I care that it's an open circle? Nope. I don't care what's happening around that, or sorry, I don't care what's happening at that value, I care what's happening around that value. The limit as x goes to -2 from the right direction. So from here, that's +1. So what can I say about the full limit at -2? Does not exist. Remember, left side has to match right side for it to exist. So 8 from the left. 8 from the left, +7. What about 6 total? Okay, now 6 from the right looks like it's 5. 6 from the left looks like it's -5. So it does not exist. But you might be thinking, well, wait a sec. What about that point right there? What about 6 comma 1? Doesn't matter. Remember, for it to exist, the left side must match the right side. And because it does not, then the limit does not exist. Okay, it doesn't matter what's happening at that point. It only matters what's happening around that point. Again, if you have any questions, feel free to stop me. Number 8. This is starting chapter 3 now, right? First couple questions of chapter 1. All the limit stuff was chapter 2. Remember, within chapter 2, we also did the definition of a limit. The limit is, well, I'm not going to even say it because we don't even need it. Because in chapter 3, we threw out that and said, okay, let's learn these derivative rules. For example, this one is the quotient rule. Remember, quotient rule is f prime g minus g prime f all over g squared. And in that g squared, I'm okay if you do not simplify it down. You do not need to simplify g squared down whenever it's a binomial or anything like that. Like this one. So let's find f prime g. Remember, f is my numerator, g is my denominator here. So f prime is 4. Derivative of 4x minus 2 is just 4. F prime g, 5x plus 1. G prime f minus g prime. Well, g prime is 5. Derivative of 5x plus 1 is just 5. So 5f, 4x minus 2. All over g squared. 5x plus 1 squared. And that's what I mean. You can FOIL that out if you'd like to, but you don't need to. I'm not going to take off points if you do not FOIL that down. All right, we distribute in the 4. So this is 20x plus 4. We distribute in a -5 here. That's -20x plus 10 all over that 5x plus 1 squared. I have the -20 and the +20 canceling out, leaving just a 14 in the numerator over 5x plus 1 squared. So if you wanted to, it would just be 14 over 25x squared plus 50x plus 1. No, I'm sorry, 10x. 25x squared plus 10x plus 1. Sorry. Questions on that one? Cool. Let's take a look at number 9 then. Find the first and second derivative. This is kind of a one that, it's I could see you overlooking the product rule. Remember that these things are multiplied together. This is not like a constant times x to the 6th. These are two different functions multiplied together. So let's take this as f and this as g. Remember, the product rule is f prime g plus g prime f. F prime g plus g prime f. Okay, f prime. The derivative of x to the 6th is 6x to the 5th. F. Or sorry, that is f. And then times g. Plus g prime f. Okay, g prime, derivative of e to the x, e to the x. And then times f, x to the 6th. Now that is completely fine. That is y prime, right? To leave it like that. I'm going to show this two different ways. The other way to write that would be if you factored out the e to the x. I remember doing this back in chapter 3. We did it this way. And I'll write this in standard form. I'll write the x to the 6th first. And then the 6x to the 5th. And do you see how I just factored out that e to the x? They both had an e to the x, so I factored out. And then I just reordered x to the 6th over, and then plus 6x to the 5th. Okay, now let me show you in this what y double prime would look like. This is the final answer for single prime, first derivative. But let's find now the second derivative. Okay, I've got two different product rules going on. They're not difficult product rules. That's why this is an okay method. All right, so f prime, this is 30x to the 4th, e to the x, f prime g, plus g prime, e to the x, f, 6x to the 5th. That is all for just that piece. Right? F prime g plus g prime f. Same thing here. Plus f prime, okay, f prime is just e to the x, g plus g prime, 6x to the 5th, f, e to the x. And then I'm just going to reorder this so that this is all in order. I'll keep the e to the x's on the left side too. So e to the x, x to the 6th, that's our first term here. And then x to the 5th, plus, we'll go 6 e to the x, x to the 5th. Next term would be x to the 4th, so this would be a plus 30 e to the x, x to the 4th. And then, oh, whoops, sorry, there were two x to the 5ths. Whoops. So that's 12. 2 6s. There we go. And then I could factor that e to the x out if you'd like to, but if you didn't do it beforehand, I'm doubting you would do it now. Because that's fine. That's totally fine to do. So what's it look? So that's y double prime. So what would that look like as the other version? Well, notice here that this is just one product rule. Just one product rule. F prime, G, plus G prime. F. Okay. And again, I can pull out that e to the x. Chances are if you did it once, you'll probably do it again. Notice that the e to the x can be factored out all the way. And then so that's an x to the 6th, 12x to the 5th, plus 30x to the 4th, which is essentially the same thing, right? If I remove the e to the x, there's the x to the 6th, 12x to the 5th, 30x to the 4th. That's a 4. There we go. Either way is fine. Either way is totally fine. Questions about that?
I have to whisper.
You good?
Yeah.
Okay. All right. Now this is a pretty difficult question. This is a weird one.
Yeah.
This is the only thing that I'm going to be asking you about implicit differentiation. We're about in November right now. Okay. This is the only question I'm going to ask you about implicit differentiation. Now, how do I know that it's even implicit differentiation? Because I'm finding the derivative with respect to x, and I'm going to have to act it on y. Okay? I'm going to have to do the derivative with respect to x on y. And that's where it gets a little funky. So let's first start to, now, how do I even know that I have to do the derivative? Well, because I want to find the equation of the tangent line. And the equation of the tangent line requires the slope at that given moment. Okay, I need the slope at 1, 0. And if I need the slope, I need the derivative. That's how I know I need to perform the derivative. All right, so let's do it. The derivative on 3x squared is just 6x. I am going to keep the 2 as a constant out in front of the derivative of xy. That's a product rule in there because x times y is a product rule. Okay, so I pulled out the constant of 2, and now I have the product of x times y. Well, okay, remember, product rule is f prime g plus g prime f. So what is my f and g in this case? Well, f is x, g is y. So f prime g, well, what's the derivative of x? 1. So it's just 1 times y, or just y. Now I've got to do g prime f. G prime. Well, what is the derivative of y? Y prime. Not 1y, no, because I'm taking the derivative with respect to x. So if I'm taking the derivative with respect to x on y, I have to write it as a y prime. So plus y prime, and then f, so x. Yes, I will have to distribute that too here in a second, but just wanted to show it just based on that. And then plus 5y. What's the derivative of 5y? 5y prime. Yeah, the y can't go away because I'm finding the derivative with respect to x. That's why this one's a weird one. 5y prime. All right, so now let's, and this is all still equal to 0. So now let's solve for y prime because y prime is my slope. Y prime is my derivative. So that's going to give me my slope. So let's solve for y prime. Let's distribute into 2. That's going to give me 6x plus 2y plus 2xy prime. I just like to reorder that. Plus 5y prime. I'm going to move everything that's not a y prime term over to the right side. So this is 2xy prime plus 5y prime. I subtract the 6x. I subtract the 2y. I factor out the y prime. Both of these terms have a y prime in them. So leaving me with a 2x plus 5. I divide over the 2x plus 5. So y prime is equal to negative 6x minus 2y over 2x plus 5. And that right there is going to give me my slope. I want to find the slope at 1, 0, right? That was the coordinate that I was given, 1, 0. So let's plug it in. Let's plug in 1, 0. That's going to be negative 6 times 1 minus 2 times 0 over 2 times 1 plus 5. So negative 6 over 2 plus 5 is 7. Negative 6/7 is my slope at 1, 0. Negative 6/7. Now it says find the equation of the tangent line. So that means I'll just go into point slope and say y minus 0 is equal to negative 6/7 x minus 1. And heck, why not? Let's just simplify it a little bit. y is equal to negative 6/7 x plus 6/7. Honestly, this would have been fine as well.
Wait, why did we do that part again?
Because I wanted to find the equation of the tangent line.
Oh,
Yeah. It wasn't enough just to find the slope. I had to then say, okay, what is the actual equation of the tangent line? Questions there? What do we got next? Oh, yeah. This one's an easy one. You just got to remember the rule for this one. Find the derivative. This is an exponential rule, right? So remember the derivative is b to the x ln b. Right, b to the x ln b, that's the exponent rule. Okay? So in this case, this is going to be 5 to the 3x squared plus 2x minus 1 times ln 5. But wait, there's more. Why? What do I have to do, Riggs?
Chain rule.
The chain rule. I have to do the chain rule because there is a function within the exponent, right? Function within another function. So I peel back the layer of the 5 to the, then I can get at the 3x squared plus 2x minus 1. So that means 6x plus 2. And that's my answer.
Wait, what?
What's wrong?
So you just found the derivative of the exponent?
Yes.
Oh, got it.
Yeah, because there was a function within the exponent. If this had been like just 5 to the x, then I wouldn't have needed to do that.
Yeah.
But because there's something else in there, I've got to multiply by the derivative of that piece.
Wait, if it was just like 5 to the x, then it would just be 5 to the x times ln of 5.
Right.
And then n.
Done.
Okay.
Right. Because then technically, if you tried to apply the chain rule, the derivative of x would just be 1. So it'd be like times 1 on the right side.
Okay.
You know what I mean?
Yeah.
Let's do 12, and then we can be done for today. Because this 13 is going to take me a while. Given the graph of the derivative, what are the intervals of increase, decrease? Identify the extreme values, state the intervals of concavity, and identify any points of inflection. This is kind of like, remember the technology section that we did, the Desmos section that we did? This is kind of how I'm going to ask that. I'm not going to ask you to do that, but this is the way I'm going to be asking you to do that. All right, so let's find intervals of increase and decrease. Now, remember that this is the graph of the derivative. This is f prime, right? Where do I locate where the original was increasing? Where it's positive, where it's above the x-axis or below the x-axis. So it's increasing from negative infinity all the way into 0.205. It is also increasing from 0.673 to infinity. Because that's everywhere where it is above the x-axis. Where it's below the x-axis is where it's decreasing. So from 0.205 to 0.673. So that must mean there are two extreme values where it crosses the x-axis. Okay, so there's going to be one at 0.205, and then there's going to be one at 0.673. What is 0.205? Is that a maximum or minimum value? It's going from increasing to decreasing, so it's a maximum, right? It's going from increasing to decreasing, so this is a max. Now, 0.673, that must be a minimum value because it's going from decreasing to increasing. It's going from down to up. So that is a minimum value. Maximum at 0.205, minimum value at 0.673. Okay, intervals of concavity. Concave up. Where do I look to see if it's concave up or concave down on that graph? I got to see where it is increasing or decreasing on that graph, right? Because concave up is basically here, where it is increasing. 0.465 to infinity. Concave down, well, that's just where this function is decreasing. So, because the slope of this is the f double prime, right? The slope of f prime is f double prime. So if the slope is positive, that means f double prime is going to be increasing. If slope is negative, that's f double prime is decreasing. If it's positive, then it's concave up. If it's negative, then it's concave down. So from negative infinity until that 0.465, which means that there is an inflection at 0.465. You look at the extreme value of f prime to find where you could have an inflection. Okay, just double check. Did I do everything? Intervals of increase and decrease. Identify the extreme values. State the intervals of concavity and identify any inflection points. Okay, checked all my boxes there. All right, so I'm going to pause there. We'll start with 13 tomorrow.